Hello, everybody, and welcome to episode 142 of I Wish You Were Dead, a podcast about things that used to be alive. My name is Gavin. That is Fia. Mike is off once again today. We are wishing him the best as he's sort of gearing up for the school year. But we have Fia with us today, and it was really important to me that Fia was with us for a couple of reasons. Number one, she just lived through a hurricane, as
Yay.
Floridians do. And, more importantly, we're talking about bivalves today, which are something of Fia's specialty, at least during her masters.
Sometimes.
Sometimes. At least going into this, you probably know, just as much or more about them than I do. I definitely am the vertebrate person, not the invertebrate person.
Yeah.
But yeah, so I wanted for sure to make sure Fia survived the hurricane just so she could be on the podcast here.
And no other reason at all.
Yeah, no other reasons. Very purely selfish. Got to do it for the content,
Yeah. Can't let the pod down.
But yeah. Yeah. So we're going to be talking about bivalves and all that entails. Are really cool. Much more interesting than someone with a vertebrate bias would be led to believe. But before we get into that, do we want to do some housekeeping real quick?
Yes, of course. As always, don't forget to rate the show on whatever platform you listen to us on, and to follow us on Twitter, Facebook, and YouTube to give us feedback about the show and any future topics you would like to hear on the pod. And if you would like to be a guest on the show, be sure to fill out our guest form, and all that stuff can be found in the show notes. And then, Gavin, what is our next episode topic?
Yeah, we are picking back up with our little series of going through each sort of time slice in Earth's history. The last one we talked about, and if I was a good content creator, I'd know which episode that is. We talked about the Eocene epoch, a time where Earth was recovering from a giant spike of greenhouse gases and was real hot at the beginning, and then started to cool off for the rest. The Earth was covered in sort of rainforest, but we're going to be talking about the epoch after that, the Oligocene or Oligocene. I've heard it pronounced both ways, and I've never been sure which one's more correct.
I like Oligocene.
That's the one that I tend to prefer. But I guess I will for sure find that out in the next 2 weeks. We're going to be talking about that in episode 143, as the Earth can sort of continue to cool on its way to the present. But that'll be next episode in about 2 weeks. Also, just real quick, speaking of hurricanes and stuff, there's a massive thunderstorm going on where I live right now. So if you hear that, if you hear some thunder in the background or just some general rain, that's why. I'm not going to say anything else because I don't want to jinx us.
We're also an ASMR podcast where you now can listen to soothing thunderstorm.
God. ASMR does the opposite for me. It freaks me out.
Yeah.
But anyway, yeah, with that awesome housekeeping out of the way, Fia, as our resident ecologist, what do you got for Seagrass Corner?
Yeah, so today on Seagrass Corner, I wanted to do something related to bivalves today because that's what we're going to be talking about. So I have a bivalve, Cardites floridanus, aka the broad rib cardidid.
That looks right.
It's a little of a mouthful, but these are a marine clam in the family Cardididae, and they can be found off the coast of Florida, Central America, South America, and the Gulf of Mexico. They're more of a square rectangular shape, but with really rounded edges, so they're just elongated. And they have a whitish color with small areas of brown arranged on the ribs. It almost looks like a checkered pattern, so of like a white background and then checkered pattern of brown. And these are tiny little guys. They usually get 18 to 38 millimeters long. And as Seagrass Corner goes, they inhabit seagrass beds, but they don't live in depths deeper than 100 feet, which I don't think seagrass even grows deeper than that anyway. So
yeah, I was going to say 100 feet seems a little deep for grass.
I mean, it happens, but...
Man, that water must just be super clear.
Yeah, exactly. There isn't really much to know about this marine clam. The only interesting thing I found about it is that according to the World Register of Marine Species, it is a species that is sensitive to disturbance, aka storms and other things.
Oh, okay.
But
gotcha.
They're probably not happy right now in my neck of the woods.
So these guys, they are like clams, right?
What does that mean, Gavin?
So, okay. As I learned through doing the research for this episode, to me, bivalve and clam were synonyms. All bivalves were clams.
No.
So this is like an actual clam.
This is an actual clam.
Okay. Yeah, so good segue here into the main topic of the episode, bivalves. Mm-hmm. Spoilers, there are different types. They're not all clams. Which I know we have talked about on the pod before, with Fia talking about her oysters. Bivalves are, if you are not familiar for some reason, they're an extremely successful group of invertebrates that are basically ubiquitous in any kind of environment in the world that has water. Pretty much, permanent water. I don't think there's really any like ephemeral bivalves. It wouldn't surprise me if there's one in some like semi-arid, freshwater environment. But for the most part, any environment that has like permanent water, there's lots and lots of bivalves. Marine, lakes, rivers, you name it. Bivalves are a group of mollusks. So mollusks are things like your cephalopods, that'd be your octopus and squid. It also includes snails and slugs, chitons, which are really neat. They're an interesting group of mollusks. If you've never heard of them, look them up. They're kind of neat. Scaphopods, which are sort of like cone-shelled mollusks. They have like a single shell, but it's very long. They're called tusk shells as well. So those are all of like the clam cousins, as well as several others. But what is included in bivalves are things like true clams, oysters, scallops, mussels, cockles, which are very similar to clams, but have kind of a more like rounded or like domed sort of shell. Basically, with a very small handful of exceptions, if it's a mollusk with two shells, it's a bivalve. Of all of the mollusks, bivalves are very diverse to begin with. For invertebrates in general are pretty much universally more diverse than vertebrates. So bivalves, there's about 20,000 species around today. Gastropods, that'd be your snails and slugs, have them beat out by quite a lot for just mollusk diversity. There's about 70,000 species of gastropods. But that includes all the ones that live on land, which there are no terrestrial bivalves. Would be an interesting sight. But yeah, so most mollusks, the things that sets bivalves apart, it's kind of in the name. Almost all mollusks that have a shell have one. With the exception of those chitons that I mentioned earlier, they have 8 that are sort of arranged in sort of like plate mail, kind of, along their back. But if it has 2, that is a bivalve. They can get a little confusing when we talk about bivalves in sort of a paleontological context, because while they're the only mollusks with 2 shells that sort of fit around the body of the animal, they're not the only animals with that body plan. They're the only mollusks, not the only invertebrates. So we'll talk much more about that in a minute. But in general, and there's always exceptions that prove the rule here. Bivalves are benthic, sessile filter feeders, like many marine invertebrates are. They sit on the bottom of the ocean, not up in the water like a fish. They tend not to move much, although more than you probably think. And they generally eat by filtering organic particles out of the water. Like I said, there are exceptions that disprove all of those. Things like scallops can fly around in the water column. There's even, I think, one genus with a couple of species of carnivorous bivalves. Mm-hmm. They can just suck whole fish into their siphon. It was kind of creepy.
Yeah. I would also say that I would have the caveat of in their adult stage, because almost every bivalve releases eggs and sperms into the water column, and then their larvae float around and move. So
yeah, that's a really good point. I don't get into their reproduction basically at all for the rest of the episode. So unlike a lot of other what most people would think of as more complex organisms, bivalves are what is considered, I think, K-selected. I'm pretty sure that's the right term. Ecologists, please confirm.
I don't know.
So basically, they have a bajillion babies and hope to overwhelm the things that eat the babies with just sheer numbers. As opposed to something like an elephant or a human, where we have very few babies but take care of them.
Right.
They do the exact opposite of that. So they basically, especially since many bivalves, once they settle, do not move, like a lot of oysters or other cementing bivalves, they stay in the same place their entire adult life. So they can't get to one another to reproduce. So they basically use, chemical signals in the water. So everybody just releases all of their sperm and eggs at the same time. They get fertilized in the water. And then they float around until they become dense enough to sink. Or in some cases, there are some free floating. We'll talk more about some of them anchor themselves to driftwood and then float around for their entire adult lives. But yes. That is generally the reproduction strategy of pretty much all bivalves. So like I said, also sort of just generally how they live. Many of them are infaunal, meaning sort of they're burrowed into the sediment on the bottom of the ocean, although that's, by no means all of them. There's others that are epifaunal, meaning they just kind of sit on top of the dirt or on top of each other. And like I said, there are some that float around attached to driftwood or other floating things. There's one specific group of bivalves called shipworms. They're called shipworms because their shells are greatly reduced. They're very, very small. But the foot, which is sort of the muscular organ that they generally use to move around, the ones that do move, is very long. It can be 6 or 7 inches long. Meanwhile, each of the valves is the size of a thumbnail.
That's cool.
Yeah, and they sort of use the valves. Valve and shell are... That's what, a single shell is called a valve. We'll talk more about terminology here in a little bit. But they sort of wiggle the valves to sort of bore holes into driftwood. They're also called teredo worms. The state fossil of, I believe, North Dakota is a teredo wood. So wood... that was floating around in the ocean that has these boreholes in it from these types of bivalves.
Cool.
So now we're going to talk about some of the parts of a bivalve, because I'm sure you're picturing one in your head, but almost 99.9% of everybody listening is picturing the shells. So we're going to talk about what's on the inside and some more details about the shell that you might not know. So, unless you are driving, put your hands together like they're each a shell of a clam. Congratulations, you have a bivalve. The most obvious part of the animal are the shells, which, like I mentioned, are called valves. They are referred to as the left valve and the right valve. We'll talk more about the shells in much more detail in a minute. On the immediate inside of the shell is an organ called the mantle. All mollusks have this, and this is what makes their shell. There's 2 ligaments, generally, or no, there's the single ligament that keeps the two valves together on sort of, that would be, I guess, along their back. It's kind of interesting to orient when you consider them, the left and the right. But yes, they have a single ligament that keeps the two together, as well as on the valves, they sort of interlock with a sort of section that are called teeth that sort of lock into each other like a zipper. And then the ligament is what like physically holds the two together. If you've ever found like a set of like connected shells on the beach with nothing in between them, the thing holding them together that after you clack it a couple of times then falls apart, that's the ligament. The mantle has two organs called siphons. One brings in water and the other lets the water back out. It's sort of like if you could only breathe in through your mouth and then out through your nose. Similar sort of deal. On the inside of the mantle are all of the various internal organs, including the gills, which are used to breathe, but they also sort of pull double duty filtering out food for the animal. These are very highly modified gills that are technically called ctenidia, I think is how you pronounce that. It's got a C at the front, which is throwing me off. Yeah. But I'm pretty sure it's ctenidia. And they're covered in these little like comb-like hairs that sort of filter food out of the water, and they cover the little food particles in mucus and then slide it down into the animal's mouth because, yes, they technically have a mouth inside their shell. Bivalves lack what in other mollusks is a pretty much ubiquitous organ called the radula. It's kind of like a spiky tongue that scrapes up food. That's what like snails and stuff. If you ever seen like a snail slithering, I guess, through like algae or something, like algae on a rock, it's basically using its radula to scrape up the algae and eat it. That's pretty much how snails and slugs eat. But bivalves don't have that because they don't really typically move as they eat, so they can't really scrape stuff. And also, if you're filter feeding, you don't really need a radula. So they don't have it anymore. Most bivalves generally have poor senses for what you are thinking of as senses, dear listeners. They have better senses than you are thinking, but the type of senses you're thinking of, generally not great for them. They don't have like this, and this is the case with a lot of invertebrates. They don't have like a head per se, but like a lot of invertebrates, they have clusters of nerves all across the inside of their body called ganglia that each sort of control a different part of the body. And they're all connected. So it's sort of like if you had like a mini brain inside each of your shoulders that each controlled one arm. That's sort of the situation they got going on. So they have separate ganglia for their foot, which is that muscular organ that they use to move around. They have a few ganglia that control the senses, some that control the internal organs, and some other muscles, and you get the idea. Most of their senses come from chemoreception, which they're very good at. That's how they talk to each other. That's how they, the main way they sort of sense their environment around them. Which when you're in the water, you can do that really easily because everybody is putting out all these chemicals all the time. That's sort of like the underwater version of smell, basically. Many have light-sensitive cells that they can pretty much just use to tell light from dark. Basically, if there's a shadow coming over top of them, that's how a lot of them, can sort of quote-unquote see, and then they'll close their shells and conceal themselves. They can't really make out shapes, but basically just a light-dark sort of thing. The main exception for this is scallops.
Yep.
Scallops actually have semi-decent vision with very unique eyes. If you want to go down a rabbit hole, definitely look up how scallop eyes work because they work very differently from your eyes.
They're also bright blue.
Yes. They're bright blue and can have up to 200 of them. And so they have these interesting double-layered retinas that basically make it so like their vision is not really like shape-based. They can't see shapes very well, but they can see contrast very, very well. So they can basically tell while they're... And it makes sense for them to have the best vision of bivalves because they're the most mobile. They move up in the water column. So if they're going to hit something, they want to know about it. And it also, they have one of the best escape mechanisms. So it makes sense that they are the best at being able to see the things that they want to escape from. So combined with all the other senses, mostly like the chemoreception, they also do have some degree of like physical touch as well. But yeah, they can change the direction of that they're swimming in the water based on like the clarity of the water. They tend to like the clearer water. But yeah, so you might think it's just sort of sitting there doing nothing, but they do have a lot of ways to, figure out what's going on in the water around them. So that's sort of generally. Do you have any other comments on the inside of the bivalves before we talk about the shells a bit more?
Bivalves have what is called an adductor muscle, which is like the piece of the scallop that you eat. If you've ever eaten a scallop, it's actually the adductor muscle, and it holds the left and right shell together, and is the predominant like the strength. It's like the muscle they use to keep themselves like closed very tightly.
Right, and in scallops they have the one big one, and like you said, that's the one that you eat. In most other bivalves, there's two that are smaller.
Right. Yeah.
So with scallops, they have the one big one because that's also how they swim.
Right. Yep.
So if you've ever looked at just like a generic seashell or a bivalve shell that you found on the beach, there's like two little circles, one on sort of each end of the inside of the shell. Those circles are where those adductor muscles go. But yeah, so let's talk a little bit more about the shell. The most sort of iconic part of the bivalve, why they're called bivalves. But I want to talk about them in contrast with one of their, I guess they're sort of cousins. They're not mollusks, but they're sort of like 1 or 2 degrees away. We've talked about them a whole bunch on this podcast. It's a group of invertebrates called brachiopods. When we're talking about bivalves in a paleontological context, you kind of have to bring up brachiopods because they are exceptionally common fossils, particularly in places like where I live in Pennsylvania, because they are marine invertebrates with 2 shells that we also call valves, that if you don't know any better, you would for sure call this a bivalve as well. Brachiopods are still around today, but we're much, much more abundant in, Earth's past than they are today. And so they get confused with bivalves a lot when specifically we're talking about like in Earth history context. The shells of bivalves, so when we're talking about the shells, I'll sort of compare and contrast a little bit here. In bivalves, the 2 valves in most species, there are exceptions, the 2 valves are more or less symmetrical with one another. That's why they're called the left and the right. If you were to cut yourself down the middle from left and right, you are more or less symmetrical. There are, like I said, some exceptions to this. Oysters tend to be much less symmetrical than some like the clams, for example, or basically any of like the cementing species, just because how they cement to one another can cause one of their valves to sort of grow in interesting shapes. But for the most part, the left valve and the right valve are basically symmetrical with one another. And that's the main distinguisher between them and brachiopods. As I've said several times, bivalves have the left and the right. In brachiopods, they have a top and a bottom. And the 2 are not symmetrical. Each half, so each single valve, is symmetrical with itself. So if you cut it in half, it is symmetrical with like its own, the left half of the top is symmetrical with the right half of the top. And so that's the main way to tell them apart On the inside, they're also very different, but we're not going to get into that. This isn't a brachiopods episode. We've had a whole episode about them in the past. And so, continuing with the shells, brachiopod shells and bivalve shells are also made out of different materials. Nearly everything that makes a hard external shell, especially in the ocean or in the water generally, makes it out of calcium carbonate. Very common. If you have like an older coffee maker, the white sort of chalky stuff that you find in your coffee maker, that is calcium carbonate. It's also called lime. You might find it in your bathtub. And so that is in basically every water supply all around the world. Some types of water, some places have more or less. But not all calcium carbonate is created equal when it is sort of made by these animals. In brachiopods, it is, when they make their shell, they sort of make it in the more traditional, quote-unquote, form called calcite. That is sort of the more stable form. But in bivalves, again with some exceptions, they generally make it out of a mix of calcite and aragonite. They are both calcium carbonate, but their atomic structure is slightly different. Where aragonite is basically a little less stable at like typical Earth conditions. So that makes it a little more susceptible to acid. So bivalve shells, all else equal, will dissolve a little more quickly than brachiopod shells. And over a very long time, like between tens of millions and hundreds of millions of years, aragonite will turn into calcite eventually. So obviously, at that time scale, that doesn't bother the bivalve at all.
Yeah.
So they make it out of this because it is just chemically a little easier for them. And just sort of we'll talk about how they make their shell a little bit because it's an interesting process. But another just little difference between brachiopods and bivalves. Mm-hmm. Bivalves, and I don't think this is the case for brachiopods. I don't think they do this. Bivalves secrete a substance called nacre, or as you've probably heard it, mother of pearl. This is that shiny, colorful structure that is sometimes on the inside of the shells, and it's also what pearls are made out of. It is a very anti-friction, so it's and their soft inside parts. They don't like stuff rubbing up against it. That's the classic example is like a grain of sand gets inside that they can't somehow get out just with their muscles. So then they just start coating it in layers of this nacre, and that's generally how pearls are thought to form. But that is pretty much a mollusk exclusive thing, nacre. Some other types of mollusks, some snails and some shelled cephalopods make that as well. Mm-hmm. The shell, when it is sort of made, because unlike something like a hermit crab that goes out and finds a shell to call home, bivalves make their shell. And when they make their shell, it is sort of, the technical term is deposited. It's deposited in layers, and that's why bivalve shells look like they have rings, because they kind of do, like a tree ring, sort of. Mm-hmm. That's actually very helpful for scientists, because you can sort of test the rings for different chemical signals to see how water chemistry has changed throughout the life of the animal. I know a bunch of people who do work with that kind of stuff. On the outside of the shell, there's sort of a layer of not quite skin, but if you've ever found a bivalve shell on the beach, it's sort of that peely film layer on the outside of the shell that's kind of like a darker color. It's called the periostracum. And it basically helps protect the animal from bacterial infection and acid corrosion from seawater is just naturally a little acidic. But that's also sort of how they grow new layers to their shell. Basically, it creates a little compartment at sort of the edge of the shell and the animal sort of pumps ions into the little compartment, the calcium and carbonate ions. And once it gets to a high enough concentration, a new ring of calcium carbonate gets deposited, and more shell forms. And so, like I said, this is that thin layer of skin type stuff that you find on the outside of a shell when you find it on the beach. So it's a really interesting method that they use to make their shells. Where the two shells are sort of joined together is called the hinge. And like I mentioned earlier, they fit together with sort of a set of teeth that lock into each other. There's different tooth orientations that we're not going to go all that deeply into. But there's just know that it's not all the same for all different, types of bivalves. There's a lot of diversity, and you might think a seemingly kind of insignificant thing, but when this is your entire protection, when that is your house, it's very important.
Fun fact. I don't know if this is for all bivalves, but it is for oysters. The point where the two shells connect at the hinge, it is called the umbo.
Yes, that is a fun that's a fun shell term.
I like that word.
Yeah. Let's see. Like I mentioned earlier, they have a ligament that holds the two together. Some of them swim, like I mentioned, like scallops. Oh, so I did have some stuff in here about the adductor muscles.
Ah, nice.
So I can skip right through that.
Cool.
They also come in a variety of shapes, these shells. As you might have noticed already, just if you can picture something like a scallop versus something like an oyster, they're very different shapes. And so the shells of bivalves generally are how we tell a lot of them apart, especially at a glance, because it's very rare that you see the inside of a living bivalve, the average person. So the shape generally is influenced by what they do for a living. The ones that live in the sediment generally have sort of elongated shells. There's a whole group of bivalves called razor shells that have very elongated shells that resemble blades. Let's see. Those that live the most sort of sedentary lifestyles, such as oysters, and others that cement themselves to the ocean floor. And typically they have one valve that does the cementing, which means the other, like I mentioned earlier, their valves are on the lower end of symmetrical with one another. The way they cement sort of makes the one valve sort of on the bottom grow irregularly, just for the, to fit whatever's around it. The bottom valve also sort of tends to be more cupped, and the other one tends to be more like a lid, so it's a little less concave. Also, fun fact, in the cementing species, it is pretty standard that like all of like a certain oyster species, it's like almost always the right valve that cements. From what I read, you can confirm or deny that.
I don't know.
Okay. But yeah, they tend to have a preference for which side does the cementing.
It doesn't surprise me. I just don't know.
Yeah. Which is the case in a lot of biology. Like handedness is very common. In like snails, for example, it is not random which way the shell curls in a snail. There is like left-handed and right-handedness in snails. There's also bivalve shells that can also be kind of spiked. Like they can have like little spines on them, or they can have sort of like extra like ruffles almost to make them harder to sort of fit in the mouth of a predator. So the shell itself, on top of being like the initial defense, can also have these extra, bits and bobs on it to make it better at defending from predators. All in all, though, bivalves are an extraordinarily successful group today. Like I mentioned, found in basically anywhere there's permanent water. Whether they are cemented in place, swimming around, boring into driftwood. They also range in size from little itty baby tiny, the smallest. It didn't have a common name, I don't think, but it's Condylonucula maya, at a shell length of 0.5 millimeter. For us here in the US, that is 0.02 inches, to the giant clam found over around like Indonesia and in sort of the Indo-Pacific, that can have a shell over 4 feet across and weigh up to like over 400 pounds.
That's on my bucket list to see one of those giant clams.
So cool.
Yeah.
They also, in their mantle, have photosynthetic symbiotes like coral do. And so they're bright colored and they do photosynthesis like coral does. Very neat. Mm-hmm. And so they range from teeny tiny to huge, and they can live basically just about anywhere as long as there is stuff in the water to filter out and not too much sediment in the water that it clogs up their gills. That's basically all a bivalve needs to survive. So before we move on to some fossils, do you have any last living bivalve news or thoughts?
So I guess maybe just one more fun fact that I know we don't get into much of the reproduction, but I know there was a study that came out a few years ago that showed that oyster larvae could actually hear, and they would actually be able to settle on reef sound more often than non-reef sound, I guess. So they have some sort of cues that allow them to kind of work their way over to a reef soundscape.
Interesting. So they're not like active swimmers, so they just kind of float.
Right.
And then I guess the thought is like when they hear more reef sound, they like kickstart shell production. And
they're
that's
like
what
time
makes
to
them
deposit.
drop.
Yeah.
Okay, that's cool.
Yeah.
That's cool. Awesome.
Yeah.
Bivalves are just very interesting. They're a lot more active than you think. If you've ever been like clam hunting on a beach or something, they can dig very quickly, much more quickly than you think they can. But yeah, so let's move on to some of the fossils here.
Yeah.
So, bivalves make up some of the earliest hard part fossils that we have in the entire world. Starting in the early and middle Cambrian period, so somewhere around 530, 540 million years ago. For this entire next probably like 10 to 15 minutes, I'm going to be name dropping episode numbers. As I mentioned at the beginning of this episode, we have a whole series about talking about each period in Earth's history. So I'm going to say time period and then episode whatever for the next little bit here. So Cambrian period, episode 50. Talked all about it. That's when we see the earliest bivalves. Basically, as soon as we get complex animal life with hard parts, bivalves are there basically instantly. There's only a handful of species of bivalves known from the Cambrian. I think maybe 5 or 6. And they were missing some of the features that modern bivalves have, but as I mentioned at the beginning, if it's got 2 valves and it's got the left and right symmetry, so the valves are basically the same, there's not much else that it can be. And also, just for the record, though, brachiopods also were around in the Cambrian, but as we talked about, it's easy enough to tell the two apart if you know what you're doing. So they show up very early, but are not particularly diverse right out the gate. In the Ordovician period, so around 280, I'm sorry, that should say 480, 480 million years ago, there was a big radiation of new species. We talk all about this in episode 59. Basically all the things that were not the real weirdos that were around in the Cambrian period, everything besides those real freaks, went through this really big radiation, including bivalves. And it's at this time where we see sort of the different varieties of tooth arrangements appear. So the way the two valves like sort of connect to one another. That's when they start to, this tooth arrangement is better for this lifestyle. This other tooth arrangement is better for this lifestyle. So that kind of shows up. One of the first sort of new adaptations that we get from them. In the Silurian period, episode 66, which is around 440 million years ago, we start to see their gills be better adapted to filter feeding. This might be potentially because getting those soft structures is very difficult as fossils. I don't know how good how many good quality fossils of soft body anatomy of bivalves we have from before this. So this could be a sampling bias thing, or it could have genuinely evolved around this time. I didn't really see any evidence for it either way, so I don't really know. But at least by the Silurian, they had this, adapted tinidia structure in their gills. Throughout the Devonian and Carboniferous periods, episodes 72 and 81, respectively. So throughout the whole 120 million years, from about 420 to 300 million years ago, they developed a much more robust siphon and foot. So they were able to actually stick the siphon quite a bit out from the actual body, and a much stronger foot to be able to dig through the sediment. So this is when they first started being infaunal, deeper in the sediment, which is how many, if not most, I think, bivalves are some degree of infaunal today. And here, at this point, as we're getting toward the end of the Paleozoic era, we get a weird bit of revisionist history with the bivalves. If you look up stuff about bivalves in the Paleozoic era, which is the large section of time from the first complex multicellular fossils up to the time of the dinosaurs, you'll see brachiopods talked about much, much more often than bivalves. And while brachiopods were definitely at their peak during those times, bivalves were also right there doing great as well. It's not like they were under the foot of brachiopods. They were right there doing great the entire time as well. Brachiopods were probably more abundant and diverse, but it's not like bivalves were nowhere to be seen. That all changes, though, when the end Permian mass extinction happens, episode 89. This is around 250 million years ago. We see both brachiopods and bivalves take a really big hit. This is the biggest mass extinction in history. Overall, 90-95% of all species go extinct. So this is a really hard time to just be alive. In older writings, you'll often see that bivalves outcompeted brachiopods after this extinction and were more efficient at doing their job of being generally benthic sessile filter feeders, and therefore took over the niche from the brachiopods. However, that doesn't really line up with sort of the patterns of extinction that we see, because during the end Permian, brachiopods were hit far, far harder than bivalves were. Brachiopods lost about 96% of their species. Meanwhile, bivalves only lost about 60%. So losing 60% of your diversity is for sure bad.
Yeah.
No one wants that. But it is sure a heck of a lot better than losing 96%. And so just this new baseline diversity being higher than the brachiopods, that's generally what we consider now as to what sort of gave them a big leg up after the extinction. And then from there, the brachiopods just kind of never recovered. Still to this day. They're still around, but there's only, at most, a couple hundred species, maybe even only around 100 species that are still alive today. And then after this big extinction, a but by the time the end Permian mass extinction happened, bivalves basically looked like modern bivalves, at least, zoomed out scale. The different sort of main groups of bivalves that we see around today sort of show up mostly right after this extinction. So, for example, oysters, scallops, cockles, they show up in the Middle Triassic. So only 10 to 15 million years after this extinction. Episode 98 for more on the Triassic. Throughout the Mesozoic, they just continue doing their thing. Those groups continue to diversify and, branch into new families, subfamilies, etc. In the Cretaceous period, episode 113, so this is sort of at the tail end of the age of dinosaurs. There's one really interesting group of bivalves that shows up, and I couldn't really tell sort of which group this fell within. I think they are clams, like true clams. But it's a group called the rudists. And they became major reef builders because they form large colonies, made enormous reefs. Like Great Barrier Reef size reefs, made mostly of these bivalves. And, they became extremely common in parts of what today is the Caribbean, as well as in parts of what is today the Middle East. And they only sort of show up at the very late Jurassic and then through to the late Cretaceous. And they were neat because they look very strange for bivalves. They had one valve, the one that was attached to the sediment or to their neighbors, like oysters do. But that valve is basically shaped like a very wide ice cream cone. And then the other valve was basically just like a little lid. So, for sure, the most asymmetrical bivalves that I'm aware of. And so, these guys kind of became a big deal because at the time, especially in those places, the water temperature and salinity were very, very high. Around 10 degrees Celsius warmer than today. Very hot. Which means corals were not having a good time. So rudists were basically there to fill in that niche of major reef builders in those specific environments. And they, as those environments started to go away toward the end of the Cretaceous, or as those sort of environmental conditions started to change, they basically didn't make it. They didn't even make it to the big extinction at the end of the Cretaceous. They went extinct before that. Not very long before that, only a few million years, if that, before the extinction. But basically, since the big asteroid came and took out the dinosaurs, bivalves have been obviously still evolving, still new species popping up and everything, but generally, broad strokes, have not had all that much of a lifestyle change or new big adaptations in the 66 million years since then. Even if new families, new species have obviously, arisen since then.
Yep.
And that's bivalves. Bivalves are very important also, and this is, I don't have this in my notes, this is just kind of off the dome. Marine invertebrates in general are extremely important to how we understand global diversity trends throughout Earth history. If pretty much all of the mass extinction numbers for during this extinction, like I mentioned with the end Permian, 96% of all species or whatever go extinct. That is almost exclusively based off of marine invertebrate data. Mostly because there's way more of those data than there is for terrestrial vertebrates. There's just, for every one terrestrial vertebrate fossil, we have thousands of marine invertebrate fossils.
Yeah.
Which is also just representative of today as well, just how the world is today. For every species of terrestrial vertebrate, there's thousands of species of marine invertebrate. So, and bivalves, particularly after the end Permian, are make up most of those data where we get extinction information from. So very, very important, very cool. My first undergraduate research project was with bivalves. So even though I do rag on them a little bit, they do have a special place in my little scientist heart.
Same.
But yeah, do you have any final closing bivalve thoughts?
Bivalves are cool. Inverts are cool.
They are. They are, and the main reason I think they're cool is because as humans, our baseline is just the things that a mammal can do or does. And there are just so many cool, weird things that invertebrates do that are just so interesting.
Yeah, totally.
And that was on a big showcase last episode talking about parasitism and all the weird invertebrate stuff there. So, but I'm rambling at this point. So this has been episode 142 of I Wish You Were Dead, a podcast about things used to be alive. My name, I guess I have been Gavin. I'm trying to think how Mike does this. I have been Gavin. That has been Fia. And we will see you all in 2 weeks. Until then, take care, everybody.
Bye.
This episode of I Wish You Were Dead was written by Gavin Davidson and hosted by Gavin Davidson, Mike Bryson, and Fenella Campanino. It was sound edited and edited for YouTube by Gavin Davidson. Special thanks to former guests of the pod and to listeners like you.